Hello everyone, welcome to our talk. So today we're going to talk about WASM Security or WebAssembly as security. So my name is Kaizhe Huang. I'm a security researcher from SysDig, and my partner Pranjal from Brave. Yes, just a little background about ourselves. So a little bit disclaimer set forth. The slides here we provide is based on our knowledge, and some of you may know WASM is still evolving very fast. So regarding the design, the implementation, they're moving very fast. So I would encourage you guys to always check the spec online so to catch up the latest change. And a quick question here. So how many of you have used WASM in production or hands-on experience with WASM? Good. Not many people. Okay. Yeah, so in today's agenda, we're going to give a quick intro about what is WASM and why WASM, and then a very simple one-on-one example about WASM, and then we'll jump into the WASM threat module, and also to see how crypto miners can be working seamlessly with WASM, and also we'll give some exploiting bugs in WASM. So what is WASM? WASM is a binary instruction format designed as a target for compilation of high-level languages like C, C++, and it's aimed to deploy on the web for client-server applications. So you can think of, oh, what is WASM? WASM basically is from a source of C, C++, or any other like high-level language, and then will become part of the JavaScript, I would say, that can be deployed directly with the web. So why we encourage people to use WASM and what's the benefit of using it. So here is a quick comparison example of between JavaScript and WASM. So we can tell that JavaScript from here it has to go through all this stage of parsing, compile, optimization, execute, etc. And then WASM just decode, compile, optimize together and execute. So in short, JavaScript is slow, and WASM is, performs much better. But does it mean that WASM is a replacement for JavaScript? Actually, it's no. So the goal of WASM here is to provide a kind of a good integration for between the backend and the front end. So a good example is that so there's some high CPU intensive task like animation or image processing. It has to happen on the web browser. So it would be good to offload this task not to do it through JavaScript, but through doing through WASM, so that it could boost the performance on your browser side, on the front end side. So WASM supports these kinds of very popular language, supports C, C++, Java, Rust, Golang, and so all this language can be converted or can be compiled into WASM. So there's a tool called EMCC. So we'll do all this compilation for you. It will help you to get into the WASM binary code directly. So and in here I want to talk about among WASM. There are some other attempts to try to achieve the to boost the web performance, like Flash, like ActiveX, and also asm.js. If you are familiar with asm.js, a little bit is compiled. It's a set of instruction compiled from JavaScript. So in order to so that the browser does not need to compile this code again, so that it can execute directly. So that will give the performance improvement a lot. So the WASM here is to try to provide a full-blown solution, so that you don't need to worry about kind of security concern, and it's more web process friendly, and also it's small. Like previous slide shows that the size of WASM module is quite small comparing to Flash or ActiveX. Okay, so let's dive into a simple example of what is WASM. So let me stop here a little bit to talk about how this conversion, the compile process look like. So a backend engineer, a C++ backend engineer, he done his work in C, C++, and he used Krypton to convert it, to compile his source code into WASM code. And so the JavaScript or the JavaScript developer can use the WASM library just like other JavaScript library, and it can be consumed by all these mainstream browsers, Firefox, Chrome, Safari, etc. Okay, so this is a very simple hello world example, C, C++, and you can tell that from after the Krypton compile. So this is this is the text format of the binary code will be used for debug purpose, but I mean by nature is the binary code. So and then from the it's called WASM, by the way. So from here, and you can see on the right side there is some JavaScript code is loading the WASM, the hello.wasm library, and then do some work and execute the simple function, simple main function hello, and then print out hello world. And regarding the WASM memory module is I would say it's quite straightforward. It composed of two parts. First, it's function table, which consists of the instruction addresses, which is there are some embedded instructions can be leveraged by the WASM and is stored in the function tables. And you also use the linear memory to store the data. We will show more example about how we can exploit the vulnerability of, or not the vulnerability of the linear memory, but some malicious usage or insecure usage of linear memory. We can see some exploit example from there. Okay, let's talk about the security aspect of WASM. So this is there's a WebAssembly link regarding the security design. Encourage you guys to take a look there. So the goal here is to, WASM by design from its nature is to aim to protect user from vulnerable or malicious code, and also provide developer primitive mitigation to write safe application. So it has this control flow integrity check. So in order by doing that to ensure the protection against control flow hijacking attacks. With that said, and also it provides the indirect function call subject to signature check. So with this help, so all this smash stack attack can be mitigated by WebAssembly or WASM. Okay, so let's look into some of these malicious modules. So you guys are much familiar with these TechCam or keylockers. So WASM can be definitely used to achieve that, to turn on your webcam, to record your keystrokes, and what makes it more interesting is that so because of the format the WASM comes up, and also the obfuscation it provides, the antivirus company are still like working on to try to detect this kind of a new threats, even though they're working very well in the traditional test game or traditional way keylogger, but from a WASM standpoint, like they're still working on to fight with this technology. And another interesting story about coin miners. So like I mentioned earlier, so WASM is good at high CPU intensive tasks. So coin mining definitely is one of them. So there's like the malicious website can embed it, like can embed it some bad coin mining WASM module, so that when user access to the website, download the WASM module, and then you start mining on user's browser, and then send it back to the coin hive. And also that the website owners share the they share the profit with the coin hive. So that's a quite interesting story here. But definitely there's some people, some malicious attackers, malicious user attackers try to use WASM to achieve the coin mining attacks. And another story about malicious Google Chrome extension contains minings using WASM as well. So a little bit more about the coin mining with WASM. So basically, a lot of the Kryptonite is one of the popular algorithms and a proof of work. It gives this, it gives the latency dependency, requires access to memory. So these are the widely adopted crypto mining algorithm was used in WASM based on observation. We still have ways to detect that thanks to the binary is quite stable, not changed too often. So which means the hash value is kind of fixed, and we can also filter out the connection to the centralized services, and with the WASM2C or WASM dump, so you can see some of this interesting field with underscore Kryptonite underscore, and people people are not seems like unlikely to modify these streams. Okay, so some other fields, some other interesting fields in the WASM module can be leveraged to detect whether there's crypto mining WASM is running on your browser. Okay, some interesting tricks. So WASM can, once the malicious WASM module load into the browser, so basically it can, open up a new browser, a new browser page, a browser window with the super tiny size, and you can even hardly find, oh, where is it on my desktop? But you can look into your CPU and then when your laptop become overheat, or you check your process list to figure out there's some anomalous process is utilizing a lot of CPU. You might want to take a look at that. Okay, now I will hand it to Pranjal to go through the vulnerable WASM modules.
Awesome. Can you hear me? Oh, awesome. Okay, that's too much. Okay, hello everyone. In the next couple of slides, we'll be looking at vulnerable WASM modules. The thing that we want to highlight over the next couple of slides is that C++ bugs can cause problems in your module. So definitely analyze your modules thoroughly before deploying them in production. Let's start with a very simple snippet. This is a very simple code which has a character array that is user control. If the user inputs a very simple ASCII string, it's printed on the screen as we see here, Mike. But what happens when this input string can be modified, and instead of like using an ASCII string, the attacker goes a little sophisticated and tries for like a format string here. The problem with this is, as Kaizhe described earlier, that we have a linear model here with WebAssembly. So the attacker will be able to read the memory and hence leak the secret, as we can see here. Next, we look at buffer overflow. This is an excerpt from the WebAssembly documentation. Essentially, it says that access to the linear memory is a bound check at the linear regional level, but this does not avoid the possibility of overriding variables. So if an attacker is able to control a string, so let's look at the memory diagram here. So we have a character input followed by the user. If the user inputs a very malicious string, says BBB admin, it fills up the first part of the memory correctly, but then it overrides the user with admin. And that causes the EMCC code to be invoked. EMCC is basically an interface to connect your native code with your JavaScript environment. So it kind of leaks the secret. So what we are trying to focus here is like C++ bugs can be a problem. So definitely investigate your code before going forward. So As you can see here, the input address and the user address are at a linear difference. So any input which is not expected can cause problems in the code. Buffer overflows kind of get interesting when WebAssembly has access to the DOM. In this case, the input that we saw earlier is overridden by a series of A followed by an image. So this will essentially override the body of the DOM and cause an XSS. So similar to XSS, it can cause other bugs as well. So really be careful when you're interfacing the native code with JavaScript. Indirect functions. This is also one more good example of how buffer overflows can be a problem with WebAssembly. So this is a very simple example of a guest book where a user can type in a message. There's a message length, and based on the language, there can be translation that goes on. The user kind of sets the translation language to English. So like if the user is nice and like just prints out the payload, we can see that the message will be filled with like the hello my friend, message length will be correct, and since the translation function is set to print in English, it will print as is. But the problem again comes back to what if the user has a malicious intent and overwrites the payload with something that's not expected. So here the payload starts with overriding the message with like an alert document cookie. It then overrides the complete message, pulls up the message length with 64, and then overrides the function with a built-in function. So essentially, like EMCC provides a lot of built-in function, and these kind of attacks can be used to exfiltrate data. So like we saw earlier, instead of like a normal message, our message was overflowed so that the function address for print in English was overwritten by EMS run script, and that caused the password to be leaked. The next kind of bug that we want to look at is a type confusion. It's a very basic issue where a variable is overwritten with a user control attacker control structure, and basically whenever that functions within that structure occur, it leads to malicious code being executed. So in this case, like if you try it with GCC, it prints malicious code executed. But the good thing with WASM is like there are signature checks present. So if you try to do this with EMCC, it fails. And this happens because it tries to check for the function signature before going forward. But the problem with this is like what happens when we try to match the signature. So in this case, instead of using a double in the argument, we change it to a void. And this essentially bypasses the signature check. The reason why this happens is because the signature checks are happening at the WebAssembly layer. So they are able to, they're not able to differentiate between the granularity at the C++ layer. But this can be avoided by using a CFI flag. So always use that. And if you use that, it essentially results in a trap. To conclude this talk, we just want to highlight that offensive WebAssembly is still in its early stages, but we are seeing a lot of like evolving malicious modules. The mitigations are helpful. They are really, the WebAssembly group at W3C is also working really hard to get it in place, but they are still in progress. So definitely analyze your code. It's a shared responsibility, so look at that. If you want to look at the code snippets that we shared here, it's on the GitHub link, so feel free to check that out. Awesome. So we wrapped it up. So questions? Wow.
Any questions from the audience? Coming right on up. Hi, you mostly focused on what looked like the C++ toolchain. Are there similar mitigations and preventions for like a Golang workflow or a Rust workflow?
So we haven't looked at the Golang and Rust environment as such, but after reading the spec, I know there have been there's been work on that. But yeah, so we haven't like really investigated if the same kind of bugs exist in that toolchain as well. Sorry about that.
Are you planning on doing like a future talk, maybe on some of the lower level things like shared memory timing attacks?
Yes. So threading is one important thing that is being looked at in WebAssembly.
I mean Spectre style, not like not attacks against your own logic, but more like exploiting them as a mechanism for just more general compromise.
Yeah, that is definitely on our future research list. But yes, that's something there. Thank you.
Any more Q&A? We have plenty of time, so ask away. Well, thank you guys. It's been a pleasure.
Thank you.
Thank you.
Thank you, everyone.